What happens when quantum computers make trillion-dollar AI infrastructure obsolete overnight? Nobody expected the most expensive technology boom in human history to end this way. Right now, across America, Europe, and Asia, giant warehouses the size of entire neighborhoods are being built at a pace the world has never seen before. Inside them, millions of processors work day and night, consuming more electricity than some countries. Governments are rewriting energy policies because of them. Utility companies are spending trillions of dollars to keep them alive. Entire industries have reorganized around a single belief: that artificial intelligence will always need bigger data centers. But what if that belief is wrong? Because inside a handful of laboratories, hidden behind security checkpoints and billion-dollar research programs, scientists are working on machines that obey completely different laws of physics. Machines that, according to some researchers, could perform calculations in minutes that would take today's most powerful supercomputers thousands of years. And if they succeed, the consequences will be difficult to comprehend. The AI infrastructure boom that has transformed the global economy, the vast forests of servers, the endless rows of GPUs, the $1 trillion being poured into concrete, steel, and electricity, could suddenly face its biggest challenge yet. Not because artificial intelligence failed, but because it no longer needed the machines we built for it. For the last few years, the world has been obsessed with AI. Every major technology company has joined the race. Microsoft, Google, Amazon, Meta, and dozens of others are spending unprecedented amounts of money to secure computing power. Data centers have become the factories of the 21st century. In 2025 alone, hundreds of billions of dollars flowed into AI infrastructure. Companies rushed to buy land, secure electricity contracts, and order vast numbers of advanced chips. The logic was simple. The company with the most computing power would dominate the future. And for a while, that strategy seemed unstoppable. Every new AI model demanded more resources. Every breakthrough required larger clusters of GPUs. The industry's answer to every problem was the same: build bigger, spend more, consume more energy. But beneath the excitement, another story was unfolding. Because while the public focused on chatbots and image generators, researchers in quantum computing were quietly crossing milestones that only a few years ago sounded impossible. To understand why that matters, you first have to understand the problem nobody wants to talk about. Artificial intelligence has an appetite. Every question asked to an AI system triggers an enormous chain of computations. Every image generated, every recommendation made, every line of code written by a machine depends on physical infrastructure hidden from view. AI feels invisible, but behind the screen lies one of the largest industrial systems humanity has ever built. And that system is hungry. Data centers already consume staggering amounts of electricity. In some countries, their energy demand rivals that of entire cities. Engineers are warning that existing power grids are struggling to keep pace. New facilities face delays measured not in months, but in years, because there simply is not enough power available. The problem is growing faster than anyone predicted. What began as a software revolution is rapidly becoming an energy crisis. And that crisis has forced some of the smartest people in the world to ask an uncomfortable question. What if there is another way? That question leads directly to quantum computing. Unlike ordinary computers, which process information using bits that can exist only as zeros or ones, quantum computers use quantum bits, or qubits, which behave according to the strange rules of quantum mechanics. Through phenomena known as superposition and entanglement, quantum systems can explore many possibilities simultaneously. For decades, this idea remained trapped in laboratories and academic papers. Building a useful quantum computer seemed impossibly difficult. The machines were unstable, error-prone, and extraordinarily expensive. Even optimistic experts believed practical applications were decades away. Then, something changed. Research accelerated. Governments increased funding. Technology companies expanded their investments. Suddenly, breakthroughs that had once been separated by years began arriving one after another. IBM unveiled increasingly powerful processors. Google demonstrated experiments pointing toward quantum advantage in specialized tasks. Microsoft announced progress in entirely new architectures designed to reduce errors that had slowed the field for years. None of these announcements meant that quantum computers had replaced classical machines, not yet. But they sent a message to the industry. The timeline might be shrinking. And that possibility is enough to make investors nervous, because the greatest threat to today's AI infrastructure does not come from an AI competitor. It comes from economics. Imagine spending billions of dollars building a giant data center that is expected to operate for decades. Imagine securing land, negotiating energy contracts, and filling entire buildings with cutting-edge hardware. Now imagine discovering that within a few years, part of the work performed by those facilities could be handled by a machine occupying a tiny fraction of the space. Suddenly, the calculations change. The question is no longer whether quantum computers will replace every server in existence. Almost nobody believes that will happen overnight. The real question is much more complicated. how much of modern AI actually requires classical computing. Because much of what artificial intelligence does can be reduced to one central task: optimization. Training a neural network means searching through enormous numbers of possible solutions. Recommendation systems, logistics networks, financial models, drug discovery, and supply chain planning all depend on finding the best answer among countless possibilities. And optimization happens to be one of the areas where quantum systems may eventually offer significant advantages. If quantum hardware becomes commercially practical, even for a narrow category of problems, the effects could ripple across the entire technology industry. Companies may delay infrastructure projects. Investors may rethink trillion-dollar spending plans. Governments may redirect national strategies. And the balance of power between technology giants could shift overnight. But there is another reason the industry is paying attention: energy. The race to build AI has become a race to secure electricity. Utilities are expanding grids. Nuclear energy projects are being reconsidered. Entire regions are competing to attract data center investment while residents worry about rising energy costs. Quantum computing does not eliminate energy consumption. In fact, maintaining quantum processors requires extremely sophisticated cooling systems operating at temperatures colder than outer space. Yet many researchers believe that, for certain calculations, quantum systems could deliver far greater computational efficiency per unit of energy than classical machines. If they are right, the consequences extend far beyond Silicon Valley. Because the future of AI is no longer just a story about software. It is a story about electricity, infrastructure, physics, and geopolitics. It is a story about who controls the next generation of computing. And it is a story unfolding right now. Some experts remain skeptical. NVIDIA CEO Jensen Huang has publicly argued that practical quantum computers remain many years away. Others believe commercial breakthroughs could arrive much sooner. The truth is that nobody knows exactly when the tipping point will come. But history suggests that transformative technologies often appear impossible right up until the moment they become inevitable. The internet looked insignificant before it connected the world. Smartphones seemed unnecessary before they changed daily life. Artificial intelligence itself was dismissed countless times before becoming one of the most valuable industries on Earth. Quantum computing may follow the same path, or it may not. That uncertainty is precisely what makes this moment so fascinating. Because somewhere inside laboratories most people will never see, engineers are attempting to build machines capable of reshaping the foundations of modern computing. And if they succeed, the biggest technology investment in human history may face a future nobody expected. The age of giant AI data centers would not end with an explosion. It would end with a transition, quietly, gradually, and then all at once. The companies that recognize the shift early may define the next century. The ones that ignore it may discover that the most expensive machines ever built were designed for a world that no longer exists. And the most extraordinary part of the story is that we may already be watching the first chapter unfold.